In this math talk, we're going to continue the discussion that we were having in our last math talk about converting standard form to vertex form, from y equals ax squared plus bx plus c to y equals ax minus h squared plus k. In the last video, we used x-intercepts on our parabola. We're going to do something that's very, very similar in this one. So we're going to use what we call symmetric points. Now you might say to yourself, well, weren't the x-intercepts symmetric points? And my answer to you would be yes. They're just a very special set of them. And we can only get those when we have a quadratic relation that is factorable. But finding any other set of symmetric points is actually fairly easy. And let me walk you through this. So we're going to go through this in much the same way. We're going to start with just a general quadratic relation, y equals ax squared plus bx plus c. Then what I'm going to do is recognize something that we saw in an earlier video, that the y-intercept is c for any parabola. In other words, if you substitute 0 for x, you would get y equals c. If I were to draw a horizontal line until it cut the parabola on the other side, I would recognize, oh yeah, I have another point on the other side that's going to have the same y coordinate. Now the question is, how do I find the x-coordinate of that point? Because that's going to be symmetric about the axis of symmetry, and that should help us find the vertex, which lies right on that axis of symmetry. Well, my strategy for doing that is actually kind of clever. And I shouldn't call it my strategy because it's not mine, but the method is quite clever. I'm first going to partially factor my expression. So I'll factor out ax from the first two terms. Not the c term, but the first two terms. So I've got ax in brackets x plus b over a. Now if you have any doubts about that, I suggest you re-expand that and you'll see, I think, that you get ax squared plus bx plus c. Now we recognize that when x is 0, we get a value of c. But here's the interesting part. If I make x negative b over a, that too will give me a value of c, because the quantity inside the brackets will work out to 0. So if I put negative b over a in for x, all of the ax and the x plus b over a will vanish, and I'll be left with c. So now I have two x-coordinates of two symmetric points. I recognize that my vertex lies halfway in between those because it lies on that axis of symmetry. And so in order to get the x-coordinate of that vertex, all I have to do is recognize it's halfway in between the 0 and the negative b over a. So I use the same technique that I used last time. I take the average of 0 and negative b over a. So that means 0 plus negative b over a divided by 2, and I get negative b over 2a, which could be the most useful little tidbit that you get out of any of these videos. If you want to find the x-coordinate of the vertex of a parabola, just take the negative of b divided by 2a. And that's a great way to do it. Whether or not your teacher will allow you to do that is another story, but it's a great little check to have in your back pocket. Now, to get the y-coordinate of the vertex, I can do a little bit of heavier algebra here, but I think you'll follow this. Just to be different, I'm going to take my original equation and substitute in for xv. I get yv is equal to a negative b over 2a all squared plus b times negative b over 2a plus c. Performing a bit of an expansion, I get b squared over 4a minus 2b squared over 4a plus 4ac over 4a. You may want to do the algebra on this just to verify that that's what you get. And then I get a common way to write this expression when I gather everything over a single denominator. I show that yv is negative b squared minus 4ac all over 4a. Now, if you've talked about the discriminant before, you'll recognize that b squared minus 4ac as once again popping up as something that's pretty significant when we talk about our parabolas. If not, you'll hear the term discriminant very, very soon. So with that being said, we have an x-coordinate, we have a y-coordinate, so now we have kind of a formula for our vertex, and it's that xv, yv is negative b over 2a, negative b squared minus 4ac over 4a. It is formulaic. It may not be the way we always want to do it, but you'll see some of the advantages as we go through this video. So let's actually put it to use in an example. And we're going to try it a couple of ways. First, we've got y equals 2x squared minus 4x minus 6. Well, the first thing I'm going to do is take that 2x squared minus 4x minus 6, and I'm going to take the approach of factoring, partially factoring the first two terms. So I'm going to take you through it. So I'm going to do this one without the actual formula down to our left here. I'm actually going to do the factoring steps to show you how it comes to be. So I get y equals 2x, x minus 2, minus 6. Now I can see that when x is 0, y is equal to negative 6. So I'll plot that point. As well, at x equals 2, the quantity in the bracket goes to 0, and I'll get y equals negative 6 again. Very quickly we establish that our vertex must lie halfway between these 2 points due to the fact that those points are symmetric. And so my x-coordinate for my vertex is 0 plus 2 over 2, which is 1. My y-coordinate works out to, when I substitute in the 1, negative 8. So I can mark my vertex, which is 1, negative 8, placing my a, my h, and my k into my equation. I get that y equals 2 x minus 1 squared, subtract 8. Now if I want to use my equation that's at the bottom of the screen, it would look something like this. So using a equals 2, b equals negative 4, and c equals negative 6, and substituting, I get really just a big bedmass question that I have to perform. And calculating this, it leads me to 1 and negative 8 for a vertex, just as we had before. And so, once again, my equation is y equals 2 x minus 1 squared, subtract 8. Now, for many of you, you might find that too formulaic and you want to go with the first approach, and I think that's terrific. Let's try one more. Y equals negative 1/3 x squared minus 2x plus 1. So we will take that expression and we will common factor out the negative 1/3 x. And I'm left with, inside the bracket, x plus 6 plus 1. Well, once again, we can establish that when x is 0, y equals 1. And so we can mark that point on our graph. And at x equals negative 6, y is again equal to 1. And so now we have our two symmetric points. And so that will lead us to getting the x-coordinate of our vertex by taking the 0 plus the negative 6 over 2 for negative 3. And the y-coordinate of our vertex, substituting in the negative 3 for x, and I get y equals 4. And so I get a vertex of negative 3 and 4, and my a value is negative 1/3 from the original equation. So I simply and easily get y equals negative 1/3 x plus 3 squared plus 4. Now, it's interesting to look at the formula approach to this one, simply because it's a little bit heavier to work with. This makes an argument for doing it the way we just did it. So watch what I do here. Substituting in negative 1/3 for a, negative 2 for b, and positive 1 for c, I get this fairly full expression. Now, to make my life a little bit easier, I multiply top and bottom by 3 to eliminate that fraction of 1/3 and negative 1/3 top and bottom everywhere where I see it. And so I get that. And I've highlighted the 3 that's left over in the 2 terms in the numerator. And then it becomes a bedmass question, as I said before. And we get a vertex, as we had before, of negative 3, 4. Now, if you ask me, my opinion, our first approach was actually easier, not using the formula. And so, just to wrap it up, we have our vertex at negative 3, 4, and we have that a value of negative 1/3. So our equation simply becomes y equals negative 1/3 x plus 3 squared plus 4. So now that's 2 methods under your belt for converting from standard form to vertex form. I've got one more method that I'm going to talk about called completing the square. But at that point, it's really up to you what method you want to use for converting from standard form to vertex form. Thanks for watching.